Here we are. It's the physics video lecture. Physics 2A video lecture 36. And we're talking about thermal physics. This is chapter 10. So it'll remind us where we left off, and then we'll move ahead. So thermal physics. In fact, we went through a whole development, hot and cold, thermal expansion, temperature scales. But the constant volume gas thermometer is what I want to remind us of. And the result of that was interesting. So we discussed the constant volume gas thermometer. I'm not going to draw the picture again. We had it up there before. What we found, though, was that there's a relation between pressure and temperature that's linear. How about if we do our graph, just to remind us. So, small version. Pressure versus temperature, and there's a linear relation between the pressure and temperature, the constant volume gas thermometer. If you choose your minimum temperature to be negative 273 degrees Celsius. So that was degrees Celsius, negative 273, and that gave us the Kelvin scale, and that gave us a direct proportionality. Pressure proportional to temperature if temperature is measured in Kelvin. So I'll like to number things, right? So that's the first point. Second point is we could use the same or a similar device. So I'm going to write, we also can find, if we do the experiments, that if temperature is held constant, so if you keep the temperature constant, then an increased pressure on a gas will compress it. So pressure and volume will be inversely related. So when temperature is constant, pressure is inversely proportional to volume. V equals volume. So you have proportional to temperature and inversely proportional to volume. So you'd have pressure times volume proportional to temperature, and you get your ideal gas law that way, experimentally. Ideal gas law, PV equals nRT, or I'm going to give you the physicist's version, PV equals capital N K sub B times T. So apparently these two expressions are the same thing with different designations. N refers to the number of particles. This is the number of moles. Number of particles, and this is called the Boltzmann constant. So one or the other, but we're going to use this one because we're interested in the molecular version. That's the ideal gas law, okay? So the direct proportionality we saw, and then I'm just claiming you have the indirect proportionality to volume. Makes sense, of course, if you compress a gas, you know the volume is smaller. Yeah, so let's talk about this briefly. That is our ideal gas law. Now, since n is just a number, so continuing this, n equals number of particles. Okay. K sub B is the Boltzmann constant. look it up, but I'll write it down. I have it here in front of me. It equals, and we're going to do the units the way we always do. We have 1.38 times 10 to the minus 3. 1.38 times 10 to the minus 23. What are the units? Okay, that's what we always like to do. So what we'll do is solve for K Boltzmann here. Square brackets, we'll solve for that, so we'll have PV, P times V over N and T. Okay, the numbers are going to be dimensionless, right? So that's no problem. The pressure is newtons per meter squared. The volume is meters cubed, and the temperature is not lowercase. The temperature is Kelvin, capital K. And look at that. Cubed divided by squared is 1, so we have newtons times meters, which is joules, okay? Work. Force times displacement work, so joules. So that's joules per Kelvin. So those are our units. I'll put them here in red. Joules per Kelvin. You always want to do this, right? You always want to make sure the units are, it's always a good, what they are, it's always a good exercise. So yeah, we've got the Boltzmann constant, pressure times volume, and K Boltzmann times temperature. And an example of how we will use this, and I'll return to that. So suppose we have a closed container, okay? We've got a closed container, that means the number of particles is constant in that closed container. The Boltzmann constant is a constant. And so what we have is this equation of state, ideal gas law. We can use it between two states, 1 and 1. We'd have a container, and then we can squish it and, you know, compress it or do something to it. We can do a number of things to this closed container, and we then have the following situation. P V over T is constant, because all that's left on the right side of the equation is constants. That means we can do this. P1 V1 over T1 is equal to P2 V2 over T2. So we use it in a similar manner to our conservation laws. It gives us one equation we can solve for some unknown. If the temperatures stay the same, you know, then you just pressure 1 times volume 1, pressure 2 times volume 2. Pressure increases, volume decreases, okay? Or if these things stay, you know, if one of these stays the same and you vary the temperature, then you can say something about either the pressure or the volume, okay? So one equation, so you can solve for one unknown, but that often gives you something. I think I'll do our example right away. Good, we'll do an example. The example we'll do is that of a bubble. Say you're a scuba diver and you exhale a bubble, and you're under the water, and as it rises to the surface, it will expand. So we can do a calculation on that. In fact, using what I have right up there. This will bring some more fluid knowledge in. So the example is that, I'll just call this the bubble. So here we are, there's a surface of water, and you know, down here, fish are swimming or something, okay? So there's a little bubble here, at point 1, and then there's that bubble rises to the surface and increases in volume. Okay. And let's suppose, let the temperature be constant throughout the water. Okay. So here we have water for our picture, and here we have atmosphere. Okay, that's the interface. Good. Here's our equation. So we'll just, and temperature is the same, so immediately P1, V1, P2, V2. Okay. And what else can we write? Well, what's the pressure down here? P1 is atmospheric pressure plus rho g h. How about I use D for depth? So we're down here at a depth D. Okay. And there's the volume. And when it breaks the surface, we just have the atmospheric pressure anymore. So that would be P atmosphere times V2. So we can now solve for one unknown, and let's go ahead and solve for V2 divided by V1. Okay. So V2, I'll divide this side by V1, and I'll divide the left side by the atmospheric pressure. That's simple enough. So V2 over V1, right, I divided by V1 over here. Dividing this side by atmospheric pressure, I get 1 plus rho GD divided by the atmospheric pressure. Okay, that's not bad. You could, for example, ask what depth would double the volume? Okay, what depth would triple the volume? Well, double the volume is pretty good. The depth that would double the volume would be when rho GD over atmospheric pressure is equal to 1, right? And then we'd have 1 plus 1 on this side, and we'd have 2 on that side. So yeah, you can answer those types of questions. That's why it's best to take it, you know, to this point or this point, and then see what your unknown is. This would make a great quiz question. Okay. And I think there's one in the book where we'll do the homework on that as well. If the temperature were different, you know, it would be, you'd have to know, say, what those temperatures are. But you see, because it's Kelvin, you know, it's not going to be that much of a temperature difference. Okay, compared to 273, the difference between surface and deep water is not that much. 10 degrees, 20 degrees. Kelvin. Okay. So that's a good example for the ideal gas law. Some words here. Well, I've said them all, so you guys fill in some good words, and we'll move on. Yeah, we'll look for a couple problems of this type to put on the homework. Okay, we're going to come back to this ideal gas law. So our next topic is the molecular theory of the ideal gas law, or the kinetic theory of the ideal gas law. Now the idea is that we have a volume that has gas particles in it, and we already had the capital N for the number of particles. So we are thinking of a container. I'll draw a nice cube here. I have a side A, and A. That's a cube of volume A cubed. Okay. And this cube is full of gas particles. of gas particles is large, very, very large. So this cube contains n gas particles, and these gas particles are just bouncing around in every which way, every direction, moving randomly. But what they do is they collide with the wall. Okay. So let me number these things here. Randomly 2. We're going to imagine there are elastic collisions with the wall. With the walls. The energy is just going to be kinetic energy. So the energy of the gas particles is just energy of their individual kinetic energies. So energy is equal to the kinetic energy, and that's just the sum of all of the 1/2 mv squared, all of the little contributions of energy there. Okay. And also, these particles are so small, but if you were to compress them all, they would just fit into a tiny corner. Okay, the volume of the particles is much, much smaller than A cubed. Okay, the total volume of the particles. I'll even put this right here. Total particle volume is what I'll call it. Is got it right. Volume. Total particle volume, much, much less, or 2 less than signs, much, much less than A cubed. Okay, so what we're going to do is try to find the pressure. Find the pressure in terms of the moving particles. So we start with impulse. Impulse, and we have F delta T is delta mv. And so if we have pressure, let's say find pressure due to a collision, right, plural. So single particle, F delta T and delta mv equals mv final minus mv initial. But if it's an elastic collision where a particle just bounces and comes right back, then we have F delta T is equal to mv final minus mv initial, so that's minus 2 mv initial because it's just bouncing back. Okay, so that's minus 2 mv initial, and delta t, or we're going to write v delta t is the time it takes to go and return. Okay, so v delta t is equal to 2 times a, speed times distance, speed times time, 2 times a. So putting those together, we have F is equal to minus 2 mv. I'm just going to drop the initial and final, right? 2 mv. And then if I divide by delta t, I'm going to have, or if I 2 mv divided by delta t is equal to 2a over v. So I end up with mv squared over a. So I'm going to just take the magnitude And if I do pressure as force per area, that means P is equal to force per area. That's going to be mv squared over A, but the area is just A squared, okay? It's A times A squared, mv squared over A cubed. So that's the pressure from a single collision, so it's actually an infinitesimal pressure, but if we add them all up, we get the pressure. So let's keep going. And this was just in one direction, so we could say it was in the x direction. So we would have, for the x direction, we're going to have P times V. And it's going to cross multiply. The A cubed is V. It's going to be the sum of all of the m sub I, v sub I squared in the x direction. Okay. But x, y, and z have to be the same, right? This is a random cube, so x, y, and z are the same. But vx squared plus vy squared plus vz squared equals to v squared. Remember, for 3 components of velocity. And because of the randomness, these are all equivalent, so we actually have 3 of this vx squared is equal to v squared, which we're going to call v squared average. So we can now make a substitution. We get PV is equal to sum of all m sub I, v sub I x squared, and then we'll continue this. They're going to all be the same, so we're going to have n times m, but the 3vx squared is v squared, so it's going to be v squared average divided by 3. So this is what we're going to work with. Yeah, you can put some of these arguments here. So this is the v squared. Let's drop the average there. The reason I put the average sign here is because I've summed over all of them. Summed over all of them, and it was a total, we could have said I equals 1 to n. And so that's where I took that average right there. But you'll notice, this looks like, so we now have, this looks like ideal gas. PV is equal to n m v squared average divided by 3. Okay. And if we compare this to the ideal gas law, which has the temperature on one side, then yeah, let's compare to the ideal gas law. Compare to PV is equal to K Boltzmann temperature in Kelvin. That's telling us that the higher temperature corresponds to a higher speed of those molecules, atoms, whatever, bounce around it. Okay. So we can make this identity. We'll go ahead and put it in red. So we have K Boltzmann temperature identified with m v v squared average over 3. And we can get an expression for the speed, so molecular speeds. Okay. And this is referred to as the root mean square. So RMS equals root mean square. And we're just solving for v squared now. So we're going to end up with the square root of 3K Boltzmann temperature divided by that mass. So you guys should look in your book, find some molecular masses, and calculate these speeds. You will be amazed. Remember, it has to be in Kelvin, but these can easily be thousands of meters per second here at room temperature where we're all living. So the gas molecules in the air are moving very high, hundreds, even thousands of meters per second, very high speeds. So yeah, this is the basics of the, look at that, 2 boards, not bad. Basics of the molecular theory of the ideal gas law. And you want to plug some numbers in here, get a feel for these speeds. Do we know any numbers by heart? You guys plug them in, okay. Okay, Boltzmann, very small, 10 to the minus 23. Temperature would be like 300, room temperature is about 300 Kelvin. Yeah, it'd be 1,000, 10 to the minus 23. 27, yes. Yeah, you'll very quickly get estimates of hundreds and even thousands of meters per second. So it's the speeds of gases at room temperature. Okay. Excellent. Okay, where do we go from here? Let me check the time. Excellent. Okay. You know, we'll just estimate. We'll estimate a speed right now. Example, hydrogen. Okay, so hydrogen's a gas, room temperature. This will give us a good estimate. So we would have T, so hydrogen at room temperature. Good. So T is like close to somewhere around 300 Kelvin. Okay, Boltzmann, what did we have? 10 to the minus 23. 10 to the minus 23. 10 to the minus 23 joules per Kelvin. And then we just need the mass of a proton. And that's 10 to the minus 27, I believe. 10 to the minus 27. Yeah. Well, you know, within a factor of 2, 10 to the minus 27. So let's just keep this simple. 10 to the minus 27 kilograms. And then when we put this together, we're looking at 3 times 300, so that's about 1,000 times 10 to the minus 23. That would be 10 to the minus 20. So 3 times 10 to the minus 23 times 3 times 10 squared. And then 10 to the minus 27. So 3 times 3, that's 10. 10 to the 3, so that's 10 to the minus 20. Minus 20. Denominator, minus 27, so plus 7. Oh, I got that. Equals 10 to the 13. Back up here. 20 plus 27. Aha, close call. One take, no edit. Okay, we got this. So 10 to the minus 20 plus 27. So that's approximately square root of 10 to the 7 equals square root of 10 is 3, square root of 10 to the 6 times 10 to the 3rd. Bingo. Okay, so we're looking at something on the order of thousands, 8,000 or thousands of meters per second. There you have it. And of course, if you have, instead of a hydrogen atom, you have, say, an oxygen molecule, you're going to have some factor of order 10, which is going to slow this down, but not that much. You're still going to have hundreds of meters per second. Good, we got that example. The one more topic, I'll leave this up here and erase this. So we've got this root mean square, and of course that was an average, but not all molecules are going. So distribution of molecular speeds is the last thing I want to put up here today. Then we'll look for some homeworks. Distribution of molecular speeds. Okay. And let's see if we have a good, I'm going to use a graph out of the book here. But first we're going to remind, yeah, okay, I've got the root mean square up there. Good. And this is a number, and this is a speed axis. So V in meters per second for a given gas. First, let me just draw the graph. It will go like this. Okay. And what that means is, that there are a certain number of particles with a very slow speed, certain number, your VRMS is going to be here, and then there are numbers with very high speeds. Okay, so there's a what's called a distribution of molecular speeds. Check this out in your textbook. The distribution changes. So at a higher temperature, the distribution may go like this. So I'm going to call this T higher and this T lower temperature, without putting any specific numbers in. The point is this: you've got some very high speed molecules in your gas. If you were to remove those high speed molecules, the average would decrease, and that would mean the temperature would go down. Okay. So there's a distribution of speeds. The root mean square that we calculated here is a type of an average, and so it's close to the most probable here. Okay, so here you would have the most molecules with these speeds, and then you'd have a few very, very fast ones and some slower ones as well. But the temperature is a statistical quantity. It's related to this average quantity. So if you raise the temperature of your gas, the distribution is also going to shift. Okay. So that's where we're going to leave it in terms of the new material for this chapter. We'll just look for a couple of homework problems. that you should enjoy doing. We did some thermal expansion. And let me know in the emails if whatever problems you want to have calculated. It just occurs to me I was supposed to do some quiz problems. We'll do those next time. Okay. Next lecture I'll start off with a bunch of quizzes. But for the moment, let's see what we have here in the homework problems. So this would be homework, whatever lecture this was, right? Was this 36? Yeah. Yeah. Yes, okay. So let's see, homework 36, chapter 10. And we want to do a couple ideal gas type of problems. "37's a good one. It's about the volume. Yeah, this is a perfect one. So problem 37, volume of a weather balloon. It's very similar to my bubble problem with the fish, except it's in the atmosphere and not in the water. So because of that, very good. Good, yeah. They give enough information there. And then 39 is basically the one I just did. It's the air bubble problem underwater, so shouldn't give any trouble. And then from the kinetic theory, problem 41, I just gave you an estimate of how we use it. They're asking for the speed of an oxygen, kinetic energy of an oxygen molecule. So that's actually easier than just doing speed. Yeah. For problem 41, let's look at this thing right now. So the average kinetic energy, you don't have to. So I'll put a note here for 41. See, we have K Boltzmann temperature equals m over 3 v squared average. Okay. So we have 3 K Boltzmann temperature m v squared average. Divide both sides by 2. So this is an important point. It doesn't matter what the molecule is, because you're actually, this is the kinetic energy, average kinetic energy, and you're looking at the left side of the equation. So that's very easy to get. Okay. Let's see what else we have. And this one is really good too. We'll leave it right here. So 47 is asking what temperature gives you a speed that corresponds to the escape speed. Remember, back in gravity, escape speed is the speed that will allow you to escape from the gravitational attraction, say, of Earth. So the escape speed from Earth, the escape is something like 11,200 meters per second. And you can see the smaller the molecule for a given temperature, the higher the speed. The significance of this is that if the root mean square speed is higher than the escape speed, then you're not going to have that gas in your atmosphere. Okay, it'll just burn off. It'll leave the atmosphere. So yeah, this is a really interesting problem as well. Good, enjoy these, and next time I'll solve some problems. Remind me in the emails, Okay, I know I was supposed to do some quiz problems on the board, but we'll get those next time. Good, see you later.